Now that we've seen the definition of a Taylor polynomial centered at 0, let's go through an example to make sure it's clear how we can find the Taylor polynomial centered at 0 for a given function. In this case, that function, f of x, is equal to e to the x, and we're tasked with finding the nth degree Taylor polynomial where n can be 1, 2, 3, 4, or 5. So essentially, we want to find 5 different polynomials. One thing I want to point out is that based off of the way that we defined the Taylor polynomial centered at 0, we need to be able to find up through the fifth derivative of our function f of x evaluated at the center x equals 0. But notice here that for this function, e to the x, every single derivative is the same. It's equal to the original function e to the x. So that makes things a lot easier. And in particular, therefore, when I evaluate any of these derivatives at 0, I get e to the 0 or 1. So when I'm plugging this in to find my polynomials, I'm just going to remember that all derivatives evaluated at 0 here are 1. So as a reminder, our Taylor polynomial formula then for the first degree said that we take f of 0, which is 1, plus f prime of 0, which is 1, times x. So in this case, that would be our first degree Taylor polynomial. It would also be the line tangent to the function f of x centered at 0. So that's not a coincidence. Those are always going to be the same thing. Now, if I need to find the second degree Taylor polynomial, now we're going to go through the x squared term. The first two terms of this are identical to the ones above. So that's one thing about these Taylor polynomials. As you go to a higher degree, you continue to just tack on terms to lower degree Taylor polynomials. Plus, now I'm going to take the second derivative evaluated at 0, which is 1, divided by 2 factorial times x. To get the third degree Taylor polynomial, again, I'm going to take everything that I had from the second degree polynomial, and I'm going to add to that the third derivative at 0, which is 1, divided by 3 factorial times x cubed. And so now we see the pattern. Again, to get to the fourth degree, I take what I had for the third. Oops, sorry, these should be squares. I tack on to that the x to the fourth term, which is going to be the fourth derivative at 0, 1, divided by 4 factorial times x to the fourth. Whoops. So writing that, that's what we get. And then finally, for the fifth, again, I take my fourth degree Taylor polynomial and I tack onto that the fifth derivative at 0, which is 1, divided by 5 factorial times x to the fifth. So notice, like I said, the growing structure here. We can also see that in this instance, we didn't have to do very much work to find the derivatives. Typically, when finding a Taylor polynomial, the bulk of the work involves finding the suitable number of derivatives of f and then evaluating them at 0 in this case. So what I want to pause and do at this moment is look at some of these graphs. So remember, our function is e to the x, and we're plotting these polynomials. So I've done this elsewhere. And so notice my blue curve here is the f of x function. It's y equals e to the x. In this instance, we're looking at the first degree Taylor polynomial. So this is my graph of t1 plus t1 of x, which we said was 1 plus x. And this looks familiar as the picture of a tangent line. We can see that it touches at the x equals 0 point and looks like it follows the slope there. Now, comparing the graph of the second degree Taylor polynomial, notice that it already looks like it's a better approximation. Whereas the line didn't have any curvature. Here we see that this bends to kind of look more like y equals e to the x. If I go to the third degree Taylor polynomial, it appears to mold even better to e to the x, and in some sense where it looks close starts to broaden out a little bit further from 0. And then when we get to the fourth, we can start to see again it's getting even better. So I stopped here with my graphs, but what I want to take away from this are two general observations. So one of these things, which you can notice as you go through the pictures, is that as you increase the degree n of the approximation of f of x by its nth degree Taylor polynomial in general is going to improve. So higher degree, typically we equate with better approximation. The other thing to look at is more of a focus of, if we were to look, let's say, let's look at this one here. Fix a degree n, but think about what happens as you move x around. So what you should see in this picture, and really any of the others, is that as I move further away from 0 on the x-axis, the gap, the vertical distance between the blue and the red curves increases. So that's where our approximation becomes not as good, it worsens. So that's the second idea for fixed n. As we plug in values further away from the center, the approximation of f of x by t sub n of x in general worsens. So those are things that are going to extend. I noted that later we're going to talk about a Taylor polynomial centered really anywhere. And so this idea, moving away from x equals 0, we're just going to replace with from the center, whatever that may be. This first idea is actually going to motivate our discussion of Taylor series later, the idea that we want to get the best approximation, we want to increase n as much as possible. So we'll come back to that at a later point. And to round this out, just because our first example was somewhat simple in that all the derivatives were the same, let's look at a case where we want to find the 8th degree Taylor polynomial centered at 0, but now for the function f of x equals cosine of x. When I'm tasked with finding a polynomial, a Taylor polynomial, I generally like to set up a structure that I'm going to find a number of derivatives. And of course, what I care about is specifically how these evaluate at the center 0. So here, cosine of 0 is 1. The first derivative is negative sine of x. If I plug in 0 to that, I get 0. The second derivative is negative cosine of x. Evaluating that at 0 gives me a negative 1. And the third derivative is positive sine of x, which evaluates to 0 when I plug in 0. So technically, I need to go up through the 8th derivative here. However, this process that we're seeing here is just going to repeat, and that's the nature of cosine and likewise of sine. So the next derivative I find would send me right back up to the top of cosine. So I really only need to find these derivatives and then just notice the pattern that the coefficients here, or at least the numerators of the coefficients, are going to change between 1, 0, minus 1, 0, 1, 0, minus 1, 0. And really I could go up as far as I need, in this case only through the 8th degree, following that pattern. So what that tells me about my Taylor polynomial is that t sub 8 of x here is going to be f of 0 plus f prime of 0 times x. Now, f prime of 0 is 0, so that means that in my polynomial I won't have an x to the first power term. Its coefficient was 0. And the next coefficient is negative, so maybe let me actually write this as 1 minus 1 over 2 factorial, and that's the coefficient of x squared. The cubic term is gone because it's coefficient of 0. Then I cycle back up to the positive 1, and that's going to be over 4 factorial times x to the 4th. The x to the 5th term has coefficient 0. X to the 6th has a negative 1 over 6 factorial coefficient. X to the 7th has coefficient 0. And finally, we end with 1 over 8 factorial, x to the 8th. So here, we didn't have to find all of the derivatives, but we did have to find a few. And in general, you can see that to find an nth degree Taylor polynomial, you need only be able to find n plus 1 derivatives, or excuse me, I should say n derivatives. You also need to know the value of the function. So that's kind of the n plus first thing that you need to find. Importantly, evaluated at the center 0. So at the kind of maximal amount of work there is that we would have to find each and every one of those rather than being able to take advantage of some kind of shortcut as we have in both of these examples here.